Hi, awesome disease and public health students. I'm going to use these slides to introduce the influenza virus and Gladwin Chapter 24. So we're all familiar with the flu. Most of you have probably had it before, but it really is no joke. 20% of the world population gets infected with some sort of influenza virus every single year. And the U.S. has epidemic influenza, which means it does occur annually, usually between late December and early March. And 10 to 40% of people will get sick inside a community where there's an outbreak, and that includes schools. And that's why you need to get your flu shot every single year. There are two sort of broad families that these viruses fit under, and I like the way they kind of, there's the orthomyo, I think is how that's pronounced, which is, you can think of ordinary flu, and then paramyo, which is the more unusual stuff, like a parade of diseases, and includes kind of the big ones: measles, highly infectious, mumps, and a lot of stuff you've probably heard of. So, flu epidemic usually occurs in 4 steps, and it's pretty consistent that you'll usually see kids at school start getting sick first. That's often where outbreaks are spreading. Then that will spread to parents and other adults, who will then begin to miss work because they're sick. You see hospital admissions on the rise for pneumonia in particular, because it's a lung infection. You also have secondary infections of bacteria making their way into the lungs after the immune system's been weakened fighting off the virus. And death tends to occur in the elderly and people who are immunocompromised. So not, the kids who are getting sick at school or the adults at work. It's then spreading into the elderly. It's important to distinguish between the two as well. The real big giveaways for the flu are fatigue and weakness, and the muscle aches and high fever as well. Fever is usually the one thing that everyone kind of, once you develop that, it's like, oh boy, I got the flu. So what is a flu virus? It is a negative-stranded RNA virus, meaning that, remember, it has to have its own sort of protein to replicate its DNA first. Its RNA isn't quite ready to go as mRNA. It has that extra step. And it's in helical form, which makes sense because only RNA viruses can have DNA in helical form. It infects cells by using 2 spike proteins, very similar to how coronavirus works. They're referred to as the hemagglutinin activity, HA, and the neuraminidase activity, the NA. And these work together. The neuraminidase is all about cutting apart the protective layer, it's called mucin, that is on your upper respiratory cells. So it cuts away that protection, and that then allows the hemagglutinin proteins to bind directly to the cells and infect them. There's an acid that they bind to. These are all glycoproteins. But again, just think of it as sticking to other cells and infecting them by injecting the DNA. So your book has this interesting animation of the spike proteins, but just showing that they work together, right? Again, think of Na as the one that strips away all the protection from your cells, that mucin in particular, and then the HA is the one that does the actual infection through this celiac acid. That's what it sticks to. So hold up a minute, right? If we know all this, and we have drugs that can interfere with these proteins, they can bind to them and block them, why are there still annual flu outbreaks? And it's because flu viruses can change these proteins and exchange HA and NA proteins to form new combinations. This happens in 2 different ways. There's genetic drift, which is mutations that cause small changes in the protein structures. Your book has this interesting analogy of like you're just kind of repositioning things. It's a slight change, not a big deal. And then there's antigenic shift. That's the big one. And again, they just picture it here as it's a giant change. So imagine a giant now holding the boat on top of a mountain. It's completely different. And what happens with this is 2 different flu viruses basically exchange their proteins. They might swap an HA or an NA with each other, and it makes a new combination that has never been seen before. Human immune systems are not ready for it at all. Every single human is prone to getting it. And this often happens in animals, which is why you hear of bird flu and swine flu. And it's pretty fascinating that you basically have to have these 2, there's better images of it in a bit actually. But antigenic drift, again, is the mutations. Antigenic shift is where you have the swap. And so here it kind of is a nice little diagram where you can see the 2 viruses swapping places with each other. Whereas here in antigenic drift, you just see the slight change. But again, what I find fascinating is that in antigenic shift, what usually has to happen is a a form of flu that was in humans has to jump into an animal like a duck that also has a duck version of the flu. And those two meet each other and swap pieces, and then this jumps back into humans in a brand new form. And again, that's what we would probably refer to as bird flu, which I'll mention in a bit. So flu viruses are named after this HA and NA type combination, right? You've probably heard of the Spanish flu. We know of it as swine flu now as H1N1. And again, it's referring to the hemagglutinin and the neuraminidase proteins that are on the surface of those viruses. Spanish flu is really, really bad. It killed about 20 to 50 million people worldwide. It has one of the highest death tolls of a virus outbreak in the United States. And ironically, it's called Spanish flu, but it actually originated in Kansas on a military base. Jumped out of a pig and into humans and then spread rapidly from there. There's been a couple other major outbreaks, right? H2N2, I think it's Asian flu, or often they all have different names. But what's interesting is that you've got H1N1 popping up numerous times. This is definitely a candidate for one that is going to have multiple pandemics. This is where in 2009 it was widely known as swine flu. And a lot of people got vaccinated for it, even though it ended up not being all that widespread. Now, there's an interesting side effect to certain medications, aspirin in particular. For some reason, the way aspirin is metabolized within some people, especially children, can actually activate and make these the influenza virus in particular more effective and a lot worse. It makes it very stressful for the liver, causes edema in the brain. So never use aspirin to treat children if they have a fever, even if you don't know what's causing the fever, because there's a chance that what's causing the fever is the flu, and the flu combined with aspirin can have really bad side effects. So it's always good to use ibuprofen. No kind of side effects with flu have been shown with that to help treat the fever. So in terms of prevention and treatment, as you know, there's always an annual vaccine. Please make sure you get your vaccine this year. We're about to enter flu season. But the way the vaccine is made is kind of interesting. What they do is just basically study what are the 3 or 4 current flus that are currently making their way around the human population, all of which could become an outbreak. And they sort of pick 1 or 2 of them, and that's what they make the vaccine based off of. So it's pretty much just guesswork. In some years, they're spot on, and the one that they vaccinated for is the one that is the outbreak. In some years, that isn't the case. There are some drugs that are effective against the flu by disrupting different things. You have the adamantanes, which are essentially stop the virus from uncoating once it's infected cells. It's really only used to treat influenza A, and unfortunately, it's been so widely used that now most forms of influenza A, which includes the H1N1 swine flu, as well as the H5N1, which is bird flu, are now resistant to that drug. There's also neuraminidase inhibitors, and again, hopefully you recognize that word. That is the NA protein, the one that usually strips away that protective layer on the cells. It disrupts the function of that. It can treat all flu strains, since all flu strains have that neuraminidase protein. But there are some kind of weird neurological side effects that have been reported. And then the final part of the chapter talks about, well, what's going to be the next pandemic flu? And it's most likely going to be bird flu. Bird flu has already jumped into the human population a few times. It's pretty scary in that it does kill pretty rapidly. I think it had a 50% fatality rate for one of the outbreaks recently, but it just hasn't really taken off. And we're currently dealing with a coronavirus outbreak and pandemic. So hopefully we can keep the flu under wraps. Okay, hope that was helpful. Read the chapter and complete the reflection quiz as well after you take notes. Thanks.